into this exciting industry tutorial. Dear viewers, dear speakers, welcome to this industry tutorial proudly brought to you by Bertin Alpao. Today's session focuses on very exciting and a rapidly evolving topic of the laser light communications and aims at answering a major question. Is adaptive optics a key player for high data rate and reliable optical ground stations? Let's see. My name is Dr. Olga Ras, and it's my great honor to moderate this webinar featuring two experts from highly innovative organizations in the field, Thales Alenia Space and Aalyria. Together, we will explore recent advances, technical challenges, and the role of adaptive optics in high performance and high data rate free space optical links. I'm delighted to introduce the host of today's tutorial, Bertin Alpao, a leading designer and manufacturer of high-quality adaptive optics components and systems, including deformable mirrors, wavefront sensors, and control electronics. Thank you for joining. We look forward to these insightful discussions. We have two amazing speakers today. We let them talk, and after this, we will address all the questions from the auditorium. So please post your questions into the chat and they will be read out loud later. And without further ado, I am pleased to introduce Dr. Baris Erkmen, CTO of Aalyria, an expert in optical communications. For over 2 decades, he advances light-based systems for terrestrial, airborne, and space applications. At Aalyria, one of the most exciting newcomers in the field of the laser light communications that brings together two technologies developed by none less as Alphabet, he leads efforts to build high-speed, software-defined laser networks across all domains. Dear Baris, the entire auditorium is very much looking forward for your insights into the next generation of optical ground stations. Will all eyes and ears, the floor is yours.
Thank you, Olga. Sorry for the silence there for a minute. I want a quick confirmation that you can all see my slides. I hope that is the case. Perfect. Olga, thank you for the very kind introduction. I want to thank Bertin Alpao for inviting Aalyria to be part of this webinar. I'm Baris Erkmen, CTO at Aalyria Technologies. I'll also thank Optica for hosting us today and also moderating this panel. I look forward to being part of it. I'm going to talk today about classical laser communications. Laurent will follow with more exciting applications in quantum world, but my intention here is to provide a bit of a tutorial view on how adaptive optics can play a role in high-speed, long-range laser communications between Earth and space. Being more of a tutorial nature, I'll call myself successful if all of you walk away thinking there's at least one thing where you knew it better than I did, and one thing that maybe you hadn't thought about recently and you're inspired to think more about it. So we'll see how close I get to that goal. Okay, I'm going to start by briefly giving a little bit of background on Aalyria because I think it'll set the context as to what content is going to come later. And then I'll talk why lasercom is an interesting technology for space-based communication services. And then we'll talk about some of the challenges with doing laser communication between Earth and space and how adaptive optics plays a role in overcoming those challenges. And where it's relevant, I'll delineate the distinction between a downlink, a space to Earth link, and an uplink, a ground to space link. And then at the very end, I want to have one slide where I take a zoom out view and really talk about how the different layers of the communication stack need to play together to deliver a resilient network service that's all optical. And then at the end, I'll have some concluding remarks. Okay, Aalyria is a Silicon Valley startup. We've been around for about 3 years, and we're developing next generation cutting edge communication technologies in service of future space-based networks. We have two technology verticals that we focus on. One of them is called Spacetime, and I'm not going to talk too much about that today, but it is a network orchestration tool for very large-scale, heterogeneous, and dynamically evolving networks. The second vertical, which is more relevant to today's topic, is called Tight Beam, and it's for long-range, very high-throughput laser communication links in Earth's atmosphere. Our focus over the last 3 years have been primarily in terrestrial applications of this technology, but in the last year, we've expanded our area of focus to think how we might be able to contribute to the space ecosystem, which is why I'm here today giving this talk. All right, if we think about satellite communications, at least in the US, its history traces all the way back to the early 60s, where the first satellites provided telephony and very limited TV broadcast services. Over the decades that ensued, the throughput demand for satellite-based communications has grown exponentially. It's been roughly doubling in data rate every 3.5 years, as we've put more and more services up to be provided through satellites. We sort of crossed the 10 gigabits per second mark in the beginning of this millennium. And actually, with the Viasat-3 satellites coming online last year and in the coming years, we will have terabit per second capability to satellites in the very near future. I would call it present. And of course, with the excitement around proliferated LEO networks, which later might expand to other orbits as well, we have no reason to think that the acceleration in data rate will decrease. If anything, it will increase. And so it's necessary to think about the ground infrastructure to supply that kind of capacity to the satellite networks in space. RF-based communications are capacity limited on a single ground site, and so you need to scale your ground infrastructure in proportion to your capacity demand. And one of the reasons why optical is very exciting is because it can fundamentally break that paradigm, because any one ground station that's optical can supply the entire capacity that a network needs in space. And the diversity necessity for optical comes from the fact that you need at least one ground station with clear air weather that can talk to the network. There are sometimes cloud or other poor weather outages. But that is decoupled from data rate requirements. And so now you have a ground infrastructure that does not need to grow in proportion to your capacity needs. And that fundamental paradigm shift is exciting for operators as they think about the future needs of their networks. One of the challenges with doing laser communication between ground and space is atmospheric turbulence. Atmospheric turbulence is a non-uniform refractive index that is present in the atmosphere because of non-uniform temperature, which has various negative effects on a laser beam that's propagating through it. Of course, being in the atmosphere, it's very highly concentrated around where the ground station would be located, but it has different effects on the downlink and uplink, and so I'm going to separate that out here. If we think about the downlink for a second, we're transmitting a very nice Gaussian or truncated Gaussian beam from the satellite with a flat wavefront or a weakly focused wavefront. And it propagates through thousands of kilometers of vacuum, and it reaches the top of the atmosphere. And in the last 50 to 100 kilometers of its propagation, it encounters this non-uniform refractive index medium. Because it's such a short propagation path relative to its total path, the beam doesn't have time to really spread out much. So the beam spread is not that much more than what the diffraction limited footprint would be. However, the wavefront does wrinkle quite a bit. And so if you look at the beam that comes to your receiver and you were to look at its angular constituents, if you were to look at its plane wave components, you'd see that spread out much more than what it would be at the top of the atmosphere. And we call that angular spread. And so you'll hear that downlinks suffer from angular spread. Of course, the irradiance profile is also not uniform. It's actually a speckle pattern. And the characteristic size of that speckle is typically smaller than what would be a typical ground station for a downlink. And so if you have a single mode receiver, a single mode fiber coupled receiver, you need to correct at least the wavefront and probably also the irradiance if you really want to do a highly mode match system to get enough light into that fiber to be able to close your link. I do want to, and so an adaptive optics system in that case is an essential piece of enabling that fiber coupling. I do want to acknowledge that not all ground stations are single mode coupled. There are certainly multi-mode fiber coupled systems or even no fiber direct free space systems. Those systems might get away without an adaptive optics subsystem, but most high throughput communication architectures are implemented today in single mode fiber systems, which is why single mode coupling is generally associated with high throughput communication systems. On the uplink, the beam that we're sending out, again, is a nicely Gaussian or collimated beam, but it hits the atmosphere right in front of the transmitter. And so by the time it went 30 to 50 kilometers going up, it's already has a wrinkled phase front and a speckle pattern, and then thousands of kilometers of vacuum propagation, which means that it's going to spread far more than what the diffraction limit of the beam would be. We call that beam spread. By the time the beam reaches the satellite, not only is it footprint much larger than what the diffraction limited footprint would be, but also the speckle, the characteristic speckle, is much larger than what a feasible aperture size is for a satellite. And so a satellite terminal looking down at Earth will see a fairly uniform wavefront. It'll see a fairly uniform irradiance front, but that irradiance will be fluctuating over time, much like the way stars twinkle when you look up in the sky. And so a satellite's perspective of a laser beam coming from Earth is a twinkling star in some sense. There are some, I didn't mention this in the previous slide, there are some simulations of what a beam irradiance and phase profile might look like. In this case, I'm showing it for an uplink. But the consequence of this is that the space terminal does not need an AO subsystem. It can probably do a high performance tip tilt is enough to get light into a fiber. But on the ground side, we're going to see, I'll talk more about this in a second, there is a benefit for the ground system to pre-distort the wavefront and possibly the irradiance of the beam that it's sending up through the atmosphere so that it looks more uniform by the time it reaches the top of the atmosphere. And therefore, a pre-distortion mechanism and a pre-distortion capability enabled by AO is still a beneficial subsystem for a ground terminal, even if it's used in transmit mode. And we'll talk a lot more about what that takes and what challenges there are in doing that. On the top right here, I'm showing a very simplified diagram of what an adaptive optic system might look like. You receive your beam with a wrinkled phase front and non-uniform irradiance. You typically siphon off some photons and put it on a wavefront sensing system. I do want to acknowledge that you could do direct wavefront sensing, but you could also do indirect wavefront sensing, where you're inferring the wavefront from other measurements on the beam. But in either case, the goal is to generate an estimate of what you think the incoming wavefront of the beam is. And then you have an optic who can spatially change its phase profile such that when the incoming beam interacts with that optic, what emerges is as close as possible to a flat wavefront. That optic could be a deformable mirror. It could be a holographic plate that's programmable. It could be a photonic chip. There are many technologies available. I'm not really going to go into the various options of how you might implement an AO system. But the overall objective is to make sure you get as uniform as possible of a wavefront, and if necessary, as uniform as possible as an irradiance profile, such that it's best mode matched to propagate in fiber when it's focused onto a single mode fiber. I will say that most AO systems do phase correction and don't bother with irradiance correction, because it turns out that if you do a good job with the phase front, you're a few dB away from what would be a perfect uniform irradiance. So oftentimes that few dB is absorbed into the link budget, and the complexity of implementing the solution is not taken. But there's no reason why that couldn't also be done. You might be asking, what is the resolution I need in order to be able to do a good job with correcting the phase front? Probably not an earth-shattering result, but it's well known that that scales as the square of the diameter of the receive aperture to the characteristic scale size of the turbulence that you receive. It's referred to as the free parameter, or R naught, or spatial coherence radius. All of these are interrelated. But it scales with the square of that ratio. There is a coefficient in front of that parameter, and that coefficient could be 1 or 5 or 50. Again, I'm not going to get into what it should be, because it's very dependent on the way you estimate your wavefront and on the way that you correct your wavefront. But I do have an example of a simulated result of what the correction might do as you increase the number of modes that you're correcting. And let me take a moment to acknowledge Dr. Bryce Tennant for helping us out with these simulations. He's been collaborating with us. On the very left side, this is a case where d over r naught square is 17. And let's call it the aperture of interest is the little yellow circle at the center of each picture. Left-hand side, you have no correction, and you can see you barely get any photons through that circle. Just with tip tilts, you do a little bit better. You're correcting 10 modes, you have a decent beam shape, and you're getting some photons through. And by the time you're doing ideal phase conjugation, which you should think is in the many tens of modes being corrected, you've gotten the most photons through your aperture. And so you can see the relative progression there of what different resolution corrections would do. I also want to talk about another really important aspect of ground space laser communication, and that is point ahead angle. By the time the photon that's transmitted from a satellite has made its way all the way to the ground and is received by the terminal on the ground, the satellite has already moved enough in the sky that if you were to have transmitted a photon back up, it would completely miss the satellite by the time it reaches back on orbit. And this is because the relative velocity of a satellite to Earth is substantial enough to warrant this. And so laser communication terminals, ground systems, always transmit the beam at an angular offset relative to the beam that it's receiving from the satellite. And that angular offset is called point ahead angle. And it is greater than typically the beam divergence angle. So we're talking about a multiple beam angular offset. And so it requires active control and has its challenges associated with that. But it's also a challenge for the adaptive optics system, because now the beam that's coming down from the satellite is traversing a different atmospheric path than the beam that's going up. They share the atmosphere close to the ground terminal, but as you get further up in the atmosphere, those paths diverge, and ultimately you might be going through entirely non-overlapping paths of atmosphere. And so if you're deriving your information about the atmosphere from the beam you're receiving from the satellite, you have imperfect information with respect to the beam that's going to be going up to the satellite. And that poses some challenges when we think about precompensation, which I mentioned earlier for uplinks. Let me take a moment to put a picture in your mind what I mean by this. And so I'm going to illustrate a plot here. The x-axis is the diameter of our ground station, and we're thinking about uplink, and the y-axis is the average of radiance that you're delivering to your satellite. This is just mean. There's also obviously a fluctuation around this mean, but I'm not going to talk about that today. If I could magically remove the atmosphere, we know that the irradiance scales with the square of the diameter of the transmitter. And so in a log-log plot, that would look like a straight line, 20 dB per decade slope. Now, let's say I did a collimated beam, no precompensation. Then we would get the following purple curve. And what that purple curve tells us is that if our transmit aperture is small, we're able to track roughly the vacuum result. And then at some point, we start to diverge and we saturate. And that point of divergence occurs when your diameter of your transmit aperture reaches about the R0 value, the characteristic scale size of the atmospheric turbulence that you're encountering. Now, let's assume that we are going to apply the conjugate phase of the beam that we receive from the satellite. So we're doing pre-distortion, but we're going to pre-distort based on just what we receive from the satellite. That's the curve that we would get in that case. As a shape, it looks just like the purple, but it has two favorable characteristics that I want to highlight. One, of course, as the aperture is small, we're still tracking the vacuum result, and we eventually diverge. That point of divergence, however, has moved right compared to the collimated beam. And so you could support a factor of 2 to 5, depending on the strength of your turbulence, larger aperture when you do atmospheric precompensation based on the received beam. And second, the irradiance value, the average irradiance value that you saturate at, is higher than what it is with a collimated beam. And that could be anywhere from 3 to 10 dV, depending again on the state of the atmospheric turbulence. And so there is still benefit, even though it's imperfect to do precompensation based on the received beam. There is still benefit in the amount of average photon efficiency of what you can deliver to a spacecraft based on that. Now, if you said, no, I really can't take that, I want to be on the diffraction limited result, well, in that case, there's a solution too. If you can estimate what will happen to the beam that's going up through your atmosphere by directly looking at that path, not looking at the receive path, but looking at the transmit path, either through a guide star, or if you have a natural star that you can see that's close enough to your transmit path, then in principle, on average, you could still maintain diffraction limited power delivery by doing the optimal precompensation until you reach the resolution limit of your AO system, of course. And so there are, and that's a challenging proposition. I'm not saying that it's trivial to do that, but if that were absolutely necessary, it is still an option for precompensation systems. One other thing that I also want to spend a minute on is reciprocity. It's a really powerful concept, and I want to distinguish between perfect reciprocity and partial reciprocity. I'm showing you again a cartoon here of two terminals this time. They're facing each other. They both have AO correction capability. And if they are communicating bidirectionally, where the transmit and receive beams are counter-propagating through the same slab of turbulence that remains frozen for the duration of that propagation, then it's a well-known result that you have perfect power reciprocity. What that means is the fraction of photons that make it into terminal B's receiver single mode fiber relative to what was transmitted from terminal A's single mode fiber is equal at all times to the fraction of photons that make it into terminal A's receiver single mode fiber relative to what was transmitted from terminal B. Now, the conditions under which this holds is very general. One, it has to be, the beams have to be counter-propagating through the same turbulence, but it can be an arbitrary profile of turbulence. Anything your mind can imagine, strong in one end or the other, or uniform, whatever else. The diameter of the apertures don't matter. They can be arbitrary. And you can have arbitrary wavefront modification on either end, whether that's just tip tilt or higher order AO, good AO, bad AO, it doesn't matter. This power reciprocity holds. To put a visual to what I just said, On the right-hand side, if I were to make a scatter plot of the coupling in both directions, what that would mean is, of course, if you looked at one end, you would get very large dynamic range. You'd see 30 dB or more of fluctuations as the state of turbulence changed, but it would always sit on the y equals x line when you look at the scatter plot. And this reciprocity is a very powerful tool. It's been proven more than a decade ago. I put some references on the bottom right for you to go read if you're interested in learning more about it. When we think about applying this to ground-to-space communications, I just violated the first assumption that I stated to you. The uplink and the downlink no longer are propagating through the same turbulence. And so you don't have perfect power reciprocity. You have something like partial power reciprocity, though. It's not completely uncorrelated. And so what looked like a perfect line now might look like an ellipse, and that ellipse, will have a wider minor axis, and it actually is slightly rotated too because you have different dynamic range on the spacecraft and ground. But it's still useful. In fact, the statistical correlations, there's at least one paper, I listed it under the second bullet there, where the statistical correlation between the uplink and the downlink is used to modify the receive beam wavefront before applying a correction to the transmit beam wavefront. There's a corrector matrix they use, which depends on the statistical estimate of that correlation. And so there's still value to partial reciprocity for ground to space. And there are even other aspects in which this partial reciprocity can come in handy. All right, I'm almost done, but just before I kind of conclude here, I want to mention that AO, as powerful as it is not a single stop shop for fixing all problems with atmospheric turbulence and laser beams going through it. You really need to look at the full communication stack, and for those of you familiar, I'm thinking of the OSI stack, and really have mitigations at every layer that address what they're capable of fixing. So even with the best AO system in the physical layer, you still need a modem that at the link layer is adaptive and is capable of adjusting the information flow to match the instantaneous capacity of the link. And even with the best modem in the world, because clouds might occlude any ground site at any moment, you need a network controller that is capable of knowing the state of the network now, and also able to predict the state of the network as you look into the future and dynamically route traffic so that an Ethernet packet arrives where it needs to arrive when it needs to arrive, which ultimately is what we need for good quality of service in any space-based network. Both of these are active areas of research and development at Aalyria. Spacetime obviously is our network tool, but we also have some modem-related efforts going on. And we're excited to sort of see the full stack come together and develop a robust laser communication solution. All right, I'm going to conclude and really quickly just highlight the things I hope that you walk away with. One is AO is a really essential subsystem for particularly ground stations when we're thinking about Earth to space communications. Even if imperfect due to point-ahead angle or other imperfect wavefront estimation, AO still offers a net benefit in over not having it. And even with the most perfect AO subsystem, you still need to think about the different layers of the communication stack in order to be able to deliver a fully robust and resilient laser communication solution that would support a future operational network. And with that, Olga, I'll turn it back to you to carry us through the next steps. Thank you for your attention.
Thank you so much, Baris. I have millions of questions, and I believe the auditorium, the audience as well. But I will remind that we will address the questions after both presentations are complete. And please just post them into either Q&A or chat. We will read them out. And so, not to really postpone the next exciting talk, I would like to introduce the second speaker of today. Is Dr. Laurent de Parny, quantum system engineer at Thales Alenia Space. Laurent works on a space-based quantum communication and cryptography. He brings experience from both quantum worlds and as well as Earth observation with his PhD and solid background in radiative transfer modeling and remote sensing. At Thales Alenia Space, which is very well known major player in satellite-based technology since decades and Earth observation and science missions, Laurent contributes to cutting-edge developments and in secure quantum links. And so today he will walk us through the fundamentals of really quantum communication in application to laser light communication, including such fancy words as QKD. So Laurent, welcome to the floor. We're all attention.
Yeah, thank you very much. Do you hear me well? Okay, and you see the screen also, I guess. Okay, perfect. So thanks a lot for the invitation. And thanks, Baris. It was very interesting, by the way. And so in this presentation, I would like to speak about, this is also laser communication from space, but in the quantum regime. So this is space-based quantum communications. And I will present on behalf of my team, with whom I'm working actively since now 5 years at Thales Alenia Space. So I will try to, okay. Okay, it works. So just first, some basics of what is quantum communications. So as you know, all our numerical devices are dealing with bit, so binary digits. We exchange 0 and 1 for the classical information. And then you can transmit information in a sequence of 0 and 1. And in the quantum communication, in quantum information, we are not only speaking of these 2 bytes, but we are speaking on something that is more rich, which is richer in terms of information, because we are speaking about the linear superposition between the 2 states, 0 and 1. And particularly, if you speak about photonic quantum communications, we used to speak about the polarization of a photon. And then in quantum communication, we are exchanging a linear superposition of 2 orthogonal polarization. And so this kind of information is encoded at the single photon level. And so we will talk about communications at very, very low power, typically sub-nanowatt power. And so this information is very fragile. And as you will see, the losses are a big problem in quantum communications. And at right, you can see an arrow. So this is like a roadmap where you can see that there are 2 points. So the first point, something we are working on actively with our colleagues in Italy and in Spain, is a quantum key distribution. So this is for the cybersecurity because of the quantum computer threat that will break the RSA cryptography method that we are using on internet. So this is the first point in the timeline, but there is another point. There are much richer use cases, and we called it the quantum information network. So we are also actively working on quantum information networks that goes much further than only QKD. So quantum information, I'm talking about the future of the telecom networks, and that's exactly the topic of this presentation. So quantum information, for why? For networking of quantum computer and sensors. So we are discussing the possibility that the quantum computers will be developed, and we will need to pull them in a network for exchange of quantum information, and also for increasing the power, the performances of the quantum computers. And this is similar for the sensors. So for instance, you can think about a gravimeter or magnetometer or so on. If you pull them in a network, then you can increase the performance exponentially with respect to the number of qubits. And if you want to connect quantum computers, you will need a quantum information network. And this is based, the mechanism to exchange the information is based on quantum teleportation. So we are not exchanging the bits like I'm doing exactly at the moment with this presentation. We are not exchanging the bits, we are teleporting the information. And the teleportation has been shown in 1997 by Anton Zellinger, who won the Nobel Prize in 2020. And so this is something that in the research labs, we are able to do that. We know in research labs, we know how to do quantum teleportation. And quantum teleportation is based on quantum entanglement. And quantum entanglement, this is also something that has been studied a lot by Alain Aspect, who won the Nobel Prize in 2020. And what I would like to emphasize here is that if you share entanglement, then you can communicate quantum information by quantum teleportation. So give me entanglement, and then I will be able to teleport my quantum information toward another user. And just to recall the entanglement. So entanglement of two particles or of two photons, for instance, in the case I'm discussing here, the quantum correlations on the entanglement are such that if you measure a particle, a photon with polarization H, then Bob will measure also the polarization H. So Alice and Bob will measure the same polarization, and that's the quantum correlation. And similarly, if you measure V polarization, so vertical polarization, then Bob will get V polarization, and the correlations are very strong. And this is quantum correlations because the two photons share the same state. So this is the one state for two particles, in fact. And so entanglement is this is at the heart of this presentation. So if you have Alice and Bob, and if they want to teleport quantum information, if the distance is short, so typically to give a rough order of magnitude, we can say that if they are at less than 100 kilometers, then you can use an untung photon source. So this is a photonic source that emits pairs of untung photons. I will not explain how it works, but you can buy it on the market, for instance. There are many companies that sells this kind of source. And then you emit the untung photon pairs. You send one photon to Alice and one photon to Bob. And if they are close together, if Alice and Bob are not very far away, then it works. Because as you know, if you are using fibers, you will have the problem that the fiber absorbs the photons, and so you have a loss, typically, which is 0.2 dB per kilometers. And so this scheme here is limited in distance. And what is actively discussed and prototype in labs, in research labs, is that for larger distances, you can introduce some new elements in the chain, which are called, so the researcher called it quantum repeaters, but in the industry, we prefer to call it entanglement swapper. And because they are not, strictly speaking, they are not repeaters. They do not bring energy into the line, but they are pushing the correlations of entanglement. So people are working actively on that, and with repeaters in black cycle, you can plug repeaters and untung photon source, and then you can increase the distance up to, let's say, roughly 500 kilometers. But the problem is that in the quantum repeaters, you have losses. You have also losses on the line in the fibers. And then you cannot increase easily, at least, the distance between Alice and Bob. And why do I say that? I say that because I'm working in a space company. We are developing satellites, and we have understood that if we want to share entanglement at larger distances, typically here 2,000 of kilometers, then you need a satellite. The satellites, even if you will have, of course, lots of losses, but the satellites will have a better performance for entanglement distribution towards larger distances. And so that's something we are actively working on to put an untung photon source on board the satellite. And in fact, this is not science fiction because the Chinese researchers, the group of Jian Weipan, has has already demonstrated that you can use a low Earth orbit satellite to distribute entanglement on large distances, and they did it in 2017. And now to put numbers into losses, we can say that you roughly have 40 dBs losses per link, and you have 2 links. So 40 dBs, that means that you're losing 99.99 of the signal. And that's on 1 link. So on 2 links, you have twice, you have 80 dBs, and that means that you are losing 99.999999% of the signal. So you're losing a lot of photons, and every photon counts. Every pairs of photons counts if you want to do a teleportation, a quantum teleportation. So the picture we have in mind in Thales Alenia Space is that probably it is highly probable that Alice and Bob, the users at the end of the line, will not have a telescope in their garden. So probably there will be a mixture between the space and the ground links. And so we are investigating the performance of systems with 1 satellite, for instance, and 2 optical ground stations with quantum repeaters or entanglement swapping, as I said, and entanglement source, and then at the end of the line, Alice and Bob. And so the path is complicated because there is a lot of elements, and that's important to understand that if you want to receive the quantum signal from space, then you will have to inject this signal into a single mode fiber or a multi-mode fiber, but you will have to inject this signal at the ground into an optical fiber, and that's very complicated to do that because of the turbulence of the space links. So you can see at right a satellite that emits a signal, an optical signal. So first, the signal goes through the space vacuum, and so things are roughly fine. And then you enter into the atmosphere, and you will have, of course, absorption, diffraction, and you will have turbulence, and also the aerosols are disturbing the propagation. And you want this signal to be injected into an optical fiber, and that's exactly why we will need an adaptive optics. So when you explain this to people that are not familiar with the topic, their first reflex is to say their first idea is to amplify the signal. They said, okay, you have lots of photons, then just amplify the signal. And in fact, in quantum communication, you can't do that. That's forbidden because there is a theorem that is called the non-cloning theorem. You cannot copy paste the photons to obtain a more powerful beam. So amplify the signal, no, it's not possible. So you can say, okay, I will now increase the number of pulses per second, so the source rate, to have more possibility to increase the probability to receive the photons at the ground. And that's fine. That's something we are working on. And you can also increase the telescope aperture because you have a link budget, and the bigger the telescope, the bigger, the higher is the number of photons received at the ground. Because for small telescopes, you have something, you have a diffraction phenomenon with a divergence proportional to the wavelength over the telescope aperture, so lambda over d. And so for a fixed wavelength, if you increase the telescope aperture, then that means that the divergence will be smaller, and so you have a beam, a collimated beam, and so that means that you reduce the losses. So fine, let's build big telescopes to receive the more power we can. But the problem is that if you do that with the atmosphere, it doesn't work well. So the telescope aperture, when you increase it, and that is the graph at right, the received power first increase with the telescope aperture. So without turbulence, you have the black line. So everything is fine. The higher the telescope aperture, the higher the received power, and that's fine. But in fact, due to atmosphere, that's not true. You have a saturation-like effect due to turbulence. And at some point, increasing more the telescope aperture will not bring higher received power. And you have a saturation at roughly the coherence length, which is called the Fried parameter. You have a saturation such that if you do not use adaptive optics, then it is inefficient to increase the telescope aperture. And that's something that has been discussed previously in the previous talk, because astronomers know this effect very well. And they know that if you increase the telescope power, that does not increase, that does not give better results. So you need an adaptive optics, particularly for the picture of planets or stars. And in our case, what we want is to inject the flux, the flow into an optical fiber. And so the solution is to mitigate the turbulence with adaptive optics. And that's why we're working with Alpao Bertin. So the general scheme of an adaptive optics has been discussed in the previous talk, but I just want to recall that it involves 3 elements called the DM, deformable mirror, the reference sensor, and the real-time controller. And when you plug these 3 elements on a loop, then you can compensate for all the turbulences of the atmosphere, and then you can inject with a better performance the signal into a single mode fiber. And in fact, if you put numbers on that, adaptive optic is a game changer for quantum communication with single mode fiber coupling, because you can see on the figures at the bottom right that for 3 telescope aperture, you can reduce the coupling losses. So this is the losses at the coupling, at the interface of the single mode fiber. When you correct Zernike radial modes, then you get the higher you correct the Zernike radial mode, and the smaller are the coupling losses, and that's fine. That's exactly what we want to do. We want to reduce the coupling losses with adaptive optics. And so this is the conclusion of my talk. The takeaway message is that Thales Alenia Space is actively involved in quantum communication, in both quantum cryptography, QKD, quantum key distribution, but not only on that, also in quantum information network. So this is like the future quantum internet. And we are also actively working on that in Europe. So the space-based quantum communication are under active development in Europe within the EuroQCI program. And particularly, this topic has focused on the use of adaptive optics to reduce the losses for fiber injection. And so adaptive optics is a game changer for quantum communication because each photon counts, and then adaptive optics brings more performances. And I would like also to stress that the quantum communication test with satellites and adaptive optics are planned in the future years in 2026. And so we will be in measure to put numbers on the advantages we have with adaptive optics techniques. And I would like to thank you for your attention.
Thank you, Laurent. We're waiting then for the next edition of this tutorial to hear the numbers. Thank you. Thank you for the both speakers. And so it's time to address some questions. And I believe I will address them by the time that they have arrived. And one of the first ones, I believe it rather from the time that it came, it's more for Baris, but nevertheless, I think both speakers can really comment on this, especially as we've heard the presentation from Laurent. From Jonas Phillips. What are the optical powers of all the optical signals in use? So what you send, what you receive. Baris?
Sure. It's a great question. I'm trying to think how I can answer and not be wrong about the answer since the systems are so varied across the board. I think just to give order of magnitude numbers, though, for space to ground, typically the power levels that you would transmit from the spacecraft are single-digit watts. It depends on the orbit, of course. Like Leo is 1,000 kilometers, Geo is 36,000 kilometers. Even if you didn't have the atmosphere, we're talking about a square law that's very substantial. So these numbers vary dramatically depending on what orbit you're in. You usually do need more power going from Earth to the spacecraft because of the effects that I described, the beam spread and all. So those are probably in the tens of watts regime. For terrestrial use cases, like strictly ground to other ground or airspace assets, I think low watts are probably what would be order of magnitude correct.
Laura, maybe comment from yours, keeping in mind that you have 99.9999999% losses.
Yeah, exact. So that's mainly the problem because we are working with very low power due to the fact that we are working at the single photon level. And particularly for entanglement distribution, you have two channels. So because in quantum cryptography, you can work with only one channels with prepare and measure protocols. And then so it's easier to have a signal received. But for entanglement distribution, then you have two channels and you have twice the possibility to lose the photons. And the events where you receive the two photons of the pair, it is harder to have these events.
So do you then in the end up with also shooting more power, or do you try to basically use what you have and just use it more efficiently?
No, so as I said, you cannot increase the power.
Okay.
That's not possible in quantum communication. So you can increase the source rate, the telescope aperture, but if you increase the telescope aperture, you will need more performant adaptive optics also.
Thank you. Also the question that what role does integrated optics, like photonic integrated circuits, peaks are play, if at all? Because Baris commented that, okay, there are many ways of doing the adaptive optics. So what are the particular maybe contributions currently from the integrated optics? Baris?
It's a great question. I won't pretend to say that I know all the options, but certainly integrated photonics plays a pretty substantial role, in my opinion, in being able to do efficient compensation at scale. There is a challenge in coupling in and out of a photonic circuit efficiently, perhaps, but you can think of certain metamaterial surfaces that are able to do phase modulation across the surface efficiently. Phased arrays are another example that I think can play that role. And so those are two that come to my mind immediately, but there might be others that I'm not thinking of at the moment as well. I guess I'll mention, this is not quite in the integrated photonics realm, but I didn't mention it. You can have segmented mirror structures as well instead of one uniform deformable surface. That's also another technique that's sometimes used, and not quite integrated photonics, but definitely in the realm of smaller scale, more integrated packaging.
Laurent, maybe comment from your side on the implementation of the photonic integrated circuits and integrated optics?
Yeah, okay. So particularly on board the satellites, if you plug an entanglement photon source, it will be great to have photonic integrated circuits for that, because you will reduce something which is called the swap, size, weight, and power. and that's perfect for the space application to reduce swap.
Mm-hmm. Thank you. I think the next question is specifically for Baris. How do you weight the trade-offs between compensating with more complex adaptive optics versus DSP and use them together in a complementary manner?
Very good question. Probably many engineering hours are spent on trying to answer that question in almost every company that is pursuing this technology. I don't know that there's a single answer to that question, but I absolutely will say, as you might infer from the information in the talk that I gave, at some point the limits, the complexity of doing atmospheric compensation via AO becomes very challenging. Let's say it starts growing exponentially. And at that point, you need to start thinking about different ways of scaling if you need to scale. And that could be where I won't get into the specifics of the DSP because I want to be respectful of not giving away what's not quite ready yet. But that's where you need to really think about what are the other layers of the communication stack that can come in to start to mitigate what's left over, I'll say, from, let's say, the best AO that you can put in. Where that line is very much what I think every system engineer is racking their brain in every company right now. And I think different solutions exist in the marketplace, which makes me think that there's different trade-offs depending on the choices you make for both the physical layer and your DSP. So I don't know that I can give a more specific answer than that.
Thank you. Compromises are always complicated in life and in science.
Absolutely.
Laurent, question for you, and it's a provocative question. When will single photon-based QKD be really implemented in actual useful system? Up to my understanding, currently everyone uses attenuated lasers, right? Or do you have a bigger view?
Yeah. Okay. So for QKD, it is of course easier to use attenuated sources. So particularly for the prepare and measure protocol, then you can use an attenuated source and you can obtain a QKD use case. You can do quantum cryptography with attenuated sources, and it's not based on entanglement. And that's why when I started my talk, I said that the first point in the future, the first application could be QKD because it's easier to do QKD. If you want to go to the quantum internet will be based on quantum entanglement distribution. You have to distribute quantum entanglement to the users such that they can do quantum teleportations. So the resource of the quantum information network is definitely entanglement. So you can do tomorrow you can do QKD with attenuated sources, but you will be stuck. You cannot go to the next point, which is quantum information network. You will need to develop entangled photon sources and distribution of that, and that's it. So that's why we are not just focusing on QKD with attenuated sources. We are actively working on the next step. We are defining the future in Thales Alenia Space. We are working on entanglement distribution because we need to push that if we want to go to a quantum internet.
Thank you. I believe the next question is also to you. What is the typical rate used to improve the detected photons? Is there any setting for the duty cycle?
Yeah. Okay. So what you can do two things. You can increase the source rate, of course, but you can also work at the detector level to improve the detector rate. With the duty cycle, you can also play with the duty cycle, of course. So what we plan to do and what I think everybody is doing, we are working with what we have. We have providers of single photon detectors, and we buy their detectors and we work with that. But we are also pushing the limits of the detectors, of course. But most of the implementation we are doing now are with costs, so commercial off the shelf detectors, and then they have their own rate of measurement, with their own parameters, so the date times, the dark count rates, and so on. And so what we try to do so far is to increase the source rate instead of developing the performance, or instead of increasing the performance of the detectors. But that does not mean that we are not working on the detectors, of course, but it's easier to increase the source rate than the performances of the detectors.
Understood. Along the same line, the question, is there a minimum number of photons required at the receiver ground station for quantum com?
But, well, I will say that if you have one pair, one pair of phantom photons, then you can do something with that. But the problem is that the teleportation is probabilistic. If you give me one Antung photon pair, I will not be able to have 100% sure teleportation with this pair of Antung photon. So it's probabilistic. Sometimes it works, sometimes it doesn't work. And so the higher you receive Antung photon pairs, the higher you maximize the chance to have quantum teleportation.
I loved your call for give me the entanglement, I'll give you the teleportation. I think
thanks, but not with 100%.
I think the next question is actually a good, rather a question for advice and for both of you, and actually very nice rounding. Do you have recommendations regarding control algorithms for the fiber coupling using adaptive optics, or maybe interesting articles? Because I guess both of you are dealing with this, like recommendations for control algorithms. Baris?
I think the short answer is yes, of course. Much like probably most people in this call, I have a stack of papers that I could point to and say there are lots of gems in here. I guess what I will say generally is not only papers, there are a lot of textbooks around optimization of adaptive optics systems for single mode coupling. And those are good search terms to come up with papers. Some of them, many decades ago were written. There are also, I would recommend focusing on also for communication systems specifically, some of the papers that address the rate of updates, the bandwidth required to be able to close it, because that's also a pretty critical element of the controllers that need to run on AO systems. You can't take all the time in the world to get the photon into the fiber because bits are flying by in real time. So I don't have a specific one that I can just blurt out off the top of my head, but certainly searching for AO systems and single mode coupling and optical communications should yield a good stack of a good lead. And not to sound like I'm putting it in an advertisement, but Optica certainly has many journals, which probably are a great repository for this.
We certainly do. Thank you for mentioning. Laurent, maybe a recommendation from you, a paper or like an algorithm that would think, okay,
sure.
that was the gem.
Yeah, okay, for algorithm and more generally for adaptive optics, I used to read Onera publications because they disseminate their results and you can learn lots of things about adaptive optics in Onera publications, yes. But on algorithm, I'm not the specialist and I cannot share a reference.
Do actually both of your organizations publish? Do you publish some of your work, Laurent or Baris? Yeah? So
for
it's
sure.
possible to find and also see what you're up to.
Yes, of course, yes. On archive or in the standard journals, like the last one was in Nature Communication Physics. We publish many results, and but we publish to have discussions with colleagues and competitors also, and also to align some decisions to go in the same direction. Even if we are competitors, that's important to have a common basis to move to develop these new systems. But when we publish, there are nothing confidential, so it's more research, applied research. So low TRL. We will not publish how we develop some equipments, for instance.
That clear. That
Yeah.
is. Baris, how about you? Do you publish, or yours really being top secretive?
I mean, the nature of being a startup, I would say that publications are not sort of the thing that we focus on a lot, for good and for bad. That being said, I'll echo what Laurent said. I am present in most conferences. We do participate in workshops and panels, particularly. I'm happy to discuss the basic science and physics of any problem. I don't think that, I obviously won't and can't get into any specific implementations and particular technologies, but the fundamental aspects of understanding a problem, I think, we're all stronger for sharing our understanding and comparing notes. And so for that, I welcome any conversation if anyone wants to reach out.
This is a very nice closing remark. And with this, I would like to very much thank all the speakers. So I also read great compliments. Thanks for the great presentations. Thanks to all of you for contribution. And of course, thanks you for great thank you to Bertin Alpao for making it happen and making this tutorial available for free for everyone to listen and enjoy. There will be a record. And thank you. Enjoy your evening. It was my great pleasure to moderate these amazing speakers. I took many messages and many new and learned a lot. Thank you very much, gentlemen. Thank you very much for the audience. And with this, happy evening.
Bye
Thank you.
bye.
Bye bye.